Hey everyone, and welcome to this explainer brought to you by Forge College. I'm absolutely thrilled to be here with you today because, well, we've reached a massive milestone. This is the culmination of our Programming with Solana track, specifically wrapping up our deep dive into exploring Borsh serialization. Today, we are laying down the absolute foundation for your Capstone project. We're going to take all those fantastic defensive Rust skills you've been building and funnel them directly into a real-world project scope. So grab a coffee, get focused, and let's get ready to build something incredible.
Now, I want to kick things off by asking what seems like a really simple question. Why map out our Solana data structures before writing a single line of code? Why not just fire up the editor and let the creativity flow? Well, listen, unless your goal is to accidentally lock up thousands of user tokens in a void of corrupted bytes, which is honestly basically like building a Jenga tower on a skateboard, winging it on the blockchain is a spectacularly bad idea. When developers try to skip the planning phase on Solana, it almost always leads to a cascading disaster of shifting byte offsets, broken deserialization checks, and just frantic late-night rework. Because on the blockchain, data layout isn't just a suggestion, right? It is the literal, physical reality of your application. Okay, let's dive into this. Think of our agenda today as our architectural blueprint for the next few minutes. First, we'll tackle the Capstone challenge. Then, we'll talk about why we need blueprints, not guesswork. After that, we'll walk through the 5 implementation phases, spend some time designing the escrow schema, and wrap it all up by defining success criteria.
Let's start with Section 1, the Capstone Challenge, Bridging Security and Project Planning. If you remember our previous lesson on security and validation for Borsh serialization, we covered a ton of ground. We talked about embedding version tags, performing length checks, and applying guard predicates. Well, I want to remind you right now that those defensive deserialization skills aren't just abstract theory anymore. They are the exact, required acceptance criteria for this capstone. The security patterns you've already practiced absolutely must shape your schema design right from the start.
To really hammer this home, let's contrast 2 completely different approaches. On one side, we have the wing it strategy. Sure, it promises speed, but it absolutely delivers chaos. You write some code, then suddenly realize you need a new field, that shifts your byte offsets, which breaks your tests, which leads to massive rework. It's just a headache. On the other side, we have the contract blueprint strategy. This is the one we're using. It provides true deterministic safety. By planning your Borsh-backed data requirements first, you guarantee safe migrations and set completely objective rules for your program. It is infinitely smoother, and it's going to save you hours of frustration. That brings us to Section 2, Blueprints, not guesswork, the mental model. We need to establish the right mindset for building on Solana. I like to call this the architect's journey. Think about it for a second. You would never try to build a multi-story house without a meticulously drawn blueprint. You need to know exactly where the load-bearing walls are before you pour a single drop of concrete. Well, similarly, you do not build a Solana program without a schema contract. So let's formally define what we mean by this. A schema blueprint is a human-readable contract detailing field names, types, ownership boundaries, and validation guarantees. This definition is incredibly powerful because it draws a thick, permanent line in the sand. It separates exactly what your on-chain program is going to assert, like strict validation and invariance, from what your client-side code expects to write or migrate. It essentially guarantees that everyone and every piece of code is on exactly the same page. To actually draft one of these blueprints, you're going to need a strict checklist. First, every account type in your capstone needs its name and purpose defined. You must decide right up front between fixed versus variable length fields and explicitly state if optional values are present. You need to list out your expected invariance, and finally, you need a fixed version tag layout. So the crucial point here is that this version tag must occupy the exact same offset in every single version of your account data. Placing it predictably makes detection and branching at deserialization time totally simple and incredibly safe. Moving right along to Section 3, the 5 implementation phases, sequencing the workflow. Now that we know what a blueprint is, how do we actually execute on it? Having a step-by-step methodology is literally the secret to saving developers massive amounts of time and sanity. By doing things in the exact right order, you prevent yourself from having to write incredibly complex, messy migration logic later down the line. Let's walk through these 5 phases together. Treat your code construction just like scheduling a phased architectural build. Phase 1 is requirements and scope. That's figuring out your user stories and what state actually needs to live on-chain. Phase 2 is schema design. This is where you draft your blueprints and Rust structs. Phase 3 is program wiring, mapping that schema directly into the program template. Phase 4 is validation and testing, running those critical round-trip serialization tests. And Phase 5 is your deployment rehearsal, practicing your migrations in a safe environment before the real deal. Now, as you move through those 5 phases, I want you to keep one golden rule in your head. Short feedback loops prevent cascading changes. You really shouldn't wait until Phase 5 to realize your Phase 2 design is totally flawed. As you're wiring your program or writing your very first tests, any schema assumptions you uncover that aren't quite working out must feed back into your design phase immediately. Catching a data-sized mismatch early, that takes 5 minutes to fix. Catching it after you've written all your complex business logic, that takes days.
All right, theory is fantastic, but let's ground this in reality. Welcome to Section 4, Designing the Escrow Schema, a concrete architectural example. We're going to take everything we just talked about and apply it to a real-world scenario by drafting a blueprint for a Solana escrow account. Basically, this is an account designed to securely hold funds on-chain until a specific release instruction is called or a timeout triggers.
Let's draft this out. A proper human-readable blueprint maps field names directly to their REST types, Borsh representation, and, crucially, a size estimate. We start with our version as a single byte, then authority is a 32-byte array. The amount is an 8-byte little Indian integer, and notice the memo. It's an option wrapping a string, which means its size is variable. Simply mapping this out forces you, the developer, to actively estimate sizes and intentionally choose between fixed or variable collections before you ever write your structs. Now, what's really interesting about this approach is exactly how we handle optional data, like a beneficiary. Instead of just lazily putting an empty array full of zeros if there's no beneficiary, we explicitly use the Rust option type to wrap our 32-byte array. Why do we do this? Because explicitly encoding the presence or absence of a value maintains incredibly clear semantics for your guard checks. When Borsh deserializes this, it expects a Boolean flag first. True if the data's there, false if it's not. It's definitive, mathematically sound, and leaves absolutely no room for ambiguity. With the schema defined, we immediately draft our deserialization guard strategy. This is how we apply the security practices we learned previously right at the front door, long before any core business logic has a chance to execute. First, we read the version byte and assert it matches our expectation. Second, we perform length-aware validation to ensure the byte slice is actually big enough. Third, we apply immediate field-level predicates, like making sure an escrow amount is strictly greater than 0. And finally, we do contextual checks, like ensuring an expiration timestamp is actually in the future, not the past. Which leads us perfectly into our final section, number 5, defining success criteria, knowing exactly when you are done. The question you always have to answer is, how do I know for sure when I'm actually finished? In engineering, done shouldn't be a gut feeling. It should be a measurable fact. We have to take our abstract goals for code quality and turn them into highly specific, testable statements to prove our design actually works. So here is what that looks like in practice. Your measurable acceptance criteria should be broken down into 3 testing tiers. First, unit tests. Here, you're specifically testing for round-trip equality, meaning if you serialize a struct and then deserialize it, you get the exact same thing back. Second, versioning tests. These prove that if you throw an unknown version at your program, it fails safely, and if you provide old data, it migrates correctly. And finally, integration tests, where your client scripts run against a local test validator to prove the whole lifecycle works. When these tests pass, your human-readable blueprint is officially enforced by your Rust implementation. I want to leave you with this incredibly important quote to really sum up our core lesson today. A passing integration checkpoint proves your Borsh-backed data contract holds under real use. That right there is the ultimate goal of your Capstone. It's not just about getting the code to compile, it's about proving definitively that your data structures are resilient, safe, and behave exactly as you design them to in a live environment. So here's my final question for you. If your program was deployed to mainnet tomorrow, would your data structures protect your users, or would they create a black hole of lost tokens? Think about that for a second. You now have the tools and the mental model to formalize your blueprints and guarantee deterministic safety. This exact setup is going to feed directly into our next lesson where we start typing out those actual REST types. I want to sincerely thank Forge College for making this explainer possible. For more amazing content and to dive much deeper into this subject and tons of other fantastic Web3 topics, I highly encourage you to visit forge.college. Keep building, keep planning, and I'll see you in the next one.